Thank you guys for tuning in for another Algebra 2 online instructional lesson. Today we are going to be taking a look at our new unit, which is on systems of equations. Um, we are starting with SE.1, which is linear systems in two variables. SE.1 is something that should be pretty much entirely reviewed from Algebra 1, but there's some key concepts that we're going to use as we carry forward into a little bit new and more complicated topics that we want to make sure that we review and we nail down. So we're going to spend some time here reviewing these Algebra 1 content with systems of equations. So let's start with a definition for systems of equation. As far as we are concerned in Algebra 2, a system of equations is essentially a set of two or more equations that are going to have the same variables where we're looking for a common solution. So it's going to be a scenario that we have two or potentially more, in this case two, things that are unknown, and we can relate them in different ways. So if we actually take a look at problem 1, we can see an example where we're going to come up with a system of equations. Problem 1 says, consider an amusement park that brought in $3,100 in revenue by charging $9 for adults and $4 for children while selling 500 tickets. So basically what we have here is we have adults tickets and we have children's tickets. Between the two of them, we sold 500 tickets. So we can relate the adult and the children's tickets together in that manner. Also, in selling them for $9 for adults and $5 for children, we were able to establish $3,100 in revenue. So we can relate those in a different format, taking a look at their value. See if you can use this information to answer questions A and B, and then we'll talk about how they come together to form a system of equations. So go ahead and pause the video and answer questions A and B. Okay, so hopefully you got down a couple equations here. So in question A, it says using A for the number of adult tickets sold, and C for children, write an equation to model the number of tickets sold. Well, we know 500 tickets are sold, so if we sold A number of adult tickets and C number of children's tickets together, they must add up to be 500. So there's our first equation. Since using the same variables, write an equation for the revenue generated by sales. Remember, revenue is created when you take sales times the price. So in here we have revenue generated by the children's tickets and revenue generated by the adults tickets. So adult ticket price was $9. So every ticket costs $9. So the revenue generated by adults tickets would be 9 times A. Then the revenue generated by children's tickets would be 5 times, C. Those two together must give us a total revenue of $3,100. So these are two equations that we have here that relate the adult and children's tickets into two different expressions. Now, neither of these two equations could be solved by themselves because we were dealing with multivariables. So in C it says write an expression to show um, that both equations, there's a typo, that both equations from A and B are being considered simultaneously. So the notation that you're going to see in these notes is basically a bracket notation where A plus C is equal to 500 and 9A plus 5C is equal to 3,100. So this is telling us that we are considering both of these two equations in order to solve. In D, it says to verify that the point, and this is a coordinate, the point 150, 350 is a solution to the system of equations. Remember, 150 is an x value and 350 is a y value. So in order for this to be a solution, that means if we substitute in 150 and 350, we would have to have an equation that is equal. So let's go ahead and take the first equation and substitute in 150 for A and 350 for C. And if we need to, we can check the calculator. So 150 plus 350, we see that yes, this is in fact 500. So this point is going to work for the first equation. Let's take a look at the second equation. So 9 times 150 plus 5 times 350, which then we can also type into the calculator. So 9 times 150 plus 5 times 350 And there we do have that this is 3100. So we can verify that this point, 150, 350, is the solution to the systems of equations. Because when substituting in the x and the y values for their um, specific points, it comes out as being equal. Now, what we could also see here is that if we take this back to the context of the problem, x is technically a. I used x in place of a here and y in place of c. If in doing so, that means we had 150 of the adults tickets sold, and we had 350 of the children tickets sold. Now, what happens if I switch these around? So what happens if I take 350 plus 150? Okay, that works for the first equation, but now what happens if I take 9 times 350 plus 5 times 150? It equals 3,900. So the order of this is going to be important, that the 150 is in relationship to A, the adults' tickets, and the 350 is in relation to C, the children's tickets. So this is a system of equations. Now we didn't see how to solve the problem, but we just looked at a question where we combined two different equations. We consider them both, and we were able to use them to come up with a solution. What we are going to focus on here is three different methods in order to solve these systems of equations. And again, you did all of these methods in Algebra 1. First method is to solve the systems graphically using our technologies and our graphing calculator. So in part 2, question 2, it says solve each of the following systems by graphing. Round to 2 decimals is needed. So we want to use the graphing calculator. Now if I hit the y equals button in my graphing calculator, let me clear out anything that's in there. The only format that I can enter this in is y equals an expression. So what we want to make sure that we do with this system of equations is first we want to rewrite in terms of y. So if I rewrite the first equation in terms of y, I would be, let's say, maybe subtracting 4x. So that would give me negative 3y equals 9 minus 4x. And then dividing by a negative 3. So y equals 9. Let me redo the order. Let me put the x first. So negative 4x divided by negative 3 would make a positive 4/3 x. 9 divided by negative 3 would give me negative 3. Then I want to do the same thing for the other equation. So in this case, this one would be pretty easy to rewrite, the second equation here, because all I would have to do is add the 2x over to the other side. So y equals 2x minus 5. And so this is still a system of equations. It's just written where y is by itself. So we rewrote that format, or the format of the equation. And now we can type the equation into the graphing calculator. So 4/3 x minus 3 and 2x minus 5. Now, I can go ahead and graph this. So if I'm on the standard window, here we have the standard window, and we can see the intersection. To get that standard window, you hit zoom and 6, and we need to make sure we see the intersection where these two lines cross. Where they cross, this is going to be the solution to our equation. So in order to find that, we can hit the second key here, hit the trace button, which takes us to calculate, select intersect. It'll say first curve, make sure your cursor is on the first line, hit enter. It'll say second curve, make sure it's on the second line, hit enter. It'll ask you to guess, you don't need to worry about guessing, just hit enter one more time. And that intersection is the solution to the equation. So we can write our solutions one of two ways. You can write it as a point, 3, 1, or x equals 3, y equals 1. You'll often see me write them as two separate variables, especially when we come to solving. Either way would be okay. So we can graph these to find their solution by finding an intersection, something we've been doing throughout the year, just not in terms of systems of equations necessarily. See if you can do B now. So pause the video, rewrite the equation, graph, and see if you can find the intersection. Okay, so hopefully you got to a solution here. So rewriting the first equation, I would subtract by 3x, so y equals negative 3x plus 2. Rewriting the second equation, I would first subtract by 5x and then divide by 3. So negative 5/3 x plus 4 would be my second equation. So it doesn't necessarily have to be in this order on the right side of the equal sign, but we do want to get y by itself. This gives us two new equations, which we can then type into the calculator. So as long as we get y by itself, addition, remember addition of order and order of addition and subtraction can be changed. So you don't necessarily have to input the equations in the exact same order, as long as it's equivalent expressions. But then we can graph them. And now we do see the two intersect over here on the left side in quadrant 2. And find that intersection. Second, trace, intersect. Select both curves. You don't need to worry about guessing. And now we have solutions. So x equals negative 1.5 and y equals 6.5. Again, you could also include that as a coordinate pair. So this is a technique that we've been using to solve equations and word problems, but now we can use that to also solve systems of equations where we have multiple equations combined. The second method that we look at is, again, something that you did in Algebra 1, solving systems by substitution. So what I'm going to do is I'm actually going to give you guys some steps that we want to write through. Again, you're probably familiar with this, but we're going to jot down some steps. Excuse me, we are going to follow these steps in the solving process. So in solving a system using substitution, our first method, substitution, the first thing that we want to do is rewrite one of the equations for a given variable. So we can see here in 3 that one of the equations is already rewritten for a variable, this variable y. So if I look at 3a, it's already rewritten. If I look at 3b, that's not the case. So I would need to rewrite the equations to get one of the variables by itself. And we'd go through the algebraic process in doing that. The second step is where the substitution comes into. So it says substitute that expression into the other equation. So let's go ahead and let's do this in 3a. So already y is written by itself. Now I'm going to take the expression that y is equal to, this x plus 2, and I'm going to substitute that into the first equation for y. So that would give me 4x plus, now instead of y, I'm going to replace that with x plus 2 equal to 4. So now we should be able to see step number 3 would then be to solve for the remaining variable. So there's only one variable here. I can solve this single variable equation by combining the like terms and then subtracting 2 and dividing by 5. So x is 5 halves, or 2.5. So that gives us one of the two parts of the equation. So we do want to figure out what x is, but we also want to figure out what the other variable y is. And so that gives us step number 4, which would be to substitute what we have now, x, into an original equation, either or, to solve for the only unknown variable remaining. So the only unknown variable now is y. So what I would do is I would take this value x and substitute it into one of these two equations. I'm going to use the second equation. So y equals 5 halves plus 2. And so now 5 halves, oops, sorry, I wrote this incorrectly. X should not be 5 halves. This should actually be 2/5. So if I take back in this step, I should have divided by 5, so that would have been 2/5. So let me fix that. X is 2/5, and then the substitution would be 2/5 plus 4. Sorry, 2/5 plus 2. So 2/5 plus essentially 10/5. Y would be 12/5. So if you wrote those in exact decimal format, that would be okay as well. So you could either list that answer as two separate answers, or you could put those together as a pair. So if you wanted to put those together as coordinates, 2/5, 12/5 would be your coordinate pair. Either or would be an acceptable answer. So using that idea in the substitution method, see if you can solve part B. Okay, so hopefully you had a chance now to do part B. Remember, again, the first step we want to do here is to get one of the variables by itself. So I'm going to choose the second equation because it's probably a little bit easier here to get y by itself down there on the bottom. It doesn't necessarily mean you had to go this route, but it's fairly easy if you go this way. So negative y equals 6 minus 8, or negative 8x plus 6, because I'm subtracting the 8x from both sides. Then I would divide by negative 1, so 8x minus 6 is equal to y. Now I can take this expression for y and substitute it into the other equation. So if I take 2x plus 5 times, remember to put parentheses around 8x minus 6 because that's an entire expression that goes together. So in simplifying, I would need to distribute here. So 5 times 8 is 40. 5 times negative 6 is negative 30. And then from here, we could combine the like terms, 42x. And then I'm going to also add the 30 to the other side, equals 35. And then divide by 42, so x equals 5/6. Substituting 5/6 back into any of these equations, I can figure out the value for y. So let me go ahead and just choose this one right here. I could go back to the original equation, but remember this y equals 8x minus 6 is equivalent to the original equation. It's just written in a little different format. So y equals 8 times 5/6 minus 6. And if we wanted to do that in the calculator, we definitely could. So let's go ahead and type that out. 8 times 5 divided by 6 minus 6. And then if we want that exact answer, let's hit the math key and put it as a fraction. So y equals 2/3. So when we solve the systems of equations, we do want answers for both of the two variables. So in order to solve using substitution, we want to rewrite one of the equations in term for a variable, it doesn't matter which one, substitute that expression into the other equation. That allows us to solve for for a variable, and then substitute again in to solve for another variable, or the remaining one. Let's go ahead and take a look at substitution by elimination. Substitution by elimination is sometimes easier, sometimes it's more difficult. But if we look at a problem like, we chose problems 3, A, and B to use substitution because here in A, y was by itself. Here in B, we could get y by itself very easily. Here in 4, we could get y by itself in some of these cases, but that might give us some fractions that we may not want to work with. So what we can do instead to simplify this process, you could definitely do substitution if you wanted to. It still works, but a different option that we have is elimination. And we want to be able to use both of them because sometimes one is faster than the other. So we're going to have some steps for elimination as well. The first thing that we want to do in the elimination method is to write each equation in the same form. So notice if we take a look at 4a, we have the same variables. It's relatively the same type of equation, but the order is not the same. So we're actually going to rewrite it so that it's in the same order. So I'm going to go ahead and write this as 2x minus 3y equal to 7, and 5x plus 6y equal to 4. Now, in the elimination method, the goal is to essentially combine these two equations to make one variable disappear. So in order to do that, we use multiplication. So what we're going to do is we're going to multiply one or both of the equations by a constant that will create opposite coefficients for a variable. So if we take a look at 4a, let me look at maybe the y's. So we notice that the coefficients for one of the y's is -3, and the coefficients is for the other is 6. Well, what I really want is those coefficients to be the same number but opposites. So what could I multiply here to get the coefficients to be the same number but opposites? If you said multiplying the first by 2, you'd be correct. You could also multiply the second by 1/2, but I'm going to try to avoid fractions here if I can. So if I multiply the first equation by 2, that gives me 4x minus 6y equal to 14. We would have to multiply everything by 2. So remember, in multiplying both sides of the equation by 2, you're not changing the value of the equation. You're just changing the way that it's represented, the structure that it's written in. So the next thing that we would want to do here is to combine the two equations using an arithmetic operation that's going to allow us to solve for only one remaining variable. So if I look at both of these two equations, essentially what I can do here is I can add them. Okay, so if I add them, 4x plus 5x would give me 9x. Negative 6y plus 6y would give me 0. And so that would just be 9x on the left side of the equation. 14 plus 4 is 18, and now this gives me an equation that I can solve for. I can divide by 9, and so now I know that x is going to be equal to 2. So what we did here is we used that elimination method to get rid of one of the variables and solve for the other. And now we can do what we did in the last question. I'm sorry. We can do what we did in the last question and substitute in this x into the either equation to solve for the only remaining unknown variable. So what I'll do is I'll go back to this first equation and substitute into 2. Now I do have to do a little bit more work here. So this gives me 2 times 2 minus 3y equal to 4, or sorry, equal to 7. So I'm going to have to do a little bit more work to come up with a solution. So 2 times 2 is 4, so if I had 4 and then I subtract it from the other side, that would give me negative 3y equals 3. Then divide by negative 3, so y equals negative 1. So that does give me two solutions. Now, one thing I didn't talk about on the last question is we do have the option of going back and checking that these are solutions. So like we did in problem number 1, at the very end we verified that these were correct answers. We can do that here as well. So I can take these two solutions and type them back into the original equation. So 2 times 2 minus 3 times negative 1, that does equal 7, and so that checks out. 6 times negative 1, looking at that second equation, plus 5 times 2, does equal 4, and so both of these values solve both of those equations. This would be our correct solution. So here we are multiplying one of the equations, or both of the equations, by a constant and trying to add those two equations together to eliminate one of the variables. Then we can solve for the remaining variable and substitute to solve for the other. Let's take a look at B. Now notice that in B your notes probably say a little bit different if you copy the notes or you printed the notes off from the page. I'm not sure if I fixed them by the time they went up, but this second equation should be 1/2 x minus 2/3 y equals 1. Now, probably what a lot of people here struggle with would be fractions. So what we can do is actually get rid of the fractions first. So if I look at the first equation, I can work on getting rid of the fraction by just multiplying by a number that's going to get rid of the denominator. So if my denominators are 8 and 4, my LCD is 8, the least common denominator. So multiply everything by 8. So that would give me 5x minus 3, sorry, not 3y, but minus 6y equals 2. Now, in the second equation, I could do one of two things. I could find something that I could multiply by the denominators to get rid of the denominators, maybe 6. Or I could find a number to multiply that's going to give me the opposite as 5 as my leading coefficient for x. Or maybe find a number that I can multiply to y, the 2/3 to give me negative 2/3 to give me the opposite of negative 6, positive 6 for my coefficient to y. Let's go ahead and just do the x's because the x's are easier here. So what would I multiply to 1/2 to give me negative 5? Should be negative 10. So I'm going to multiply everything here by negative 10. It's going to give me a fraction, but one fraction is not bad. So negative 10 times 1/2 would give me negative 5x. Negative 10 times negative 2/3 would give me positive 20/3. I'm going to leave that as a fraction for now. And negative 10 times 1 would give me negative 10. Now, I can take these two equations and add them together because we'd see that the x and the negative 5x would eliminate with one another. Negative 6 is basically negative 18/3, so this would give me 2/3 y equals negative 10. So now how can I get rid of this last fraction? Well, I can multiply by 3 and then divide by 2. So y equals basically negative 30 if you multiply by 3, divided by 2. Y equals negative 15. So I have my answer for y, and now I need to find my answer for x. So I'm going to use the second equation to find the answer for x because I know that 3 divides 15 evenly. Just makes the math a little bit easier. Either equation would work. So negative 2/3 times negative 15 equals 1. So 1/2 x. Negative 2/3 times negative 15. If you need to do that in your calculator, you can. I'll go ahead and do that on this specific one so you guys can see it. Negative 2/3 times negative 15 would give me 10. So this is basically 1/2 x minus 10. So I'd add 10 to both sides, and that would give me 11. Then I'd multiply by 2 to get rid of this 1/2. So x equals 22. Again, let's check this. Let's make sure this is accurate. So 5/8 times 22 minus 3/4 times -15 equals 25. So here, I must have made an error. Let's see if we can find that error. Aha! Hopefully you guys noticed this originally when I was going through this. Sorry about making a mistake. It happens. But when I took the 2 and added it to the, or when I added these two equations together, I forgot to add the 2 and the -8. So actually 2 and -10. Actually 2 and -10 should give me -8 here. So this equation should have read 2/3 y equals -8. Hopefully you caught that. If you didn't, now let's fix it. So y would actually not be negative, I don't know, what did I have before, -15. Y would actually be a -24 divided by 2, which would be a -12. So y should be -12, and then if I substitute into either equation here, either one would work. Equal to 1, I can solve for x again, so 1/2 x equals, or 1/2 x plus 8 equals 1. So 1/2 x, let's subtract 8 on both sides. So 1/2 x equals -7. So x should equal -14. Now let's check this and make sure this one actually works out. So 5/8 times -12 minus 3/4 times -14. Shoot, over 2. Let's find this mistake. Ah, I typed it into my calculator incorrectly. So I put the y and the x in the wrong spot. So this should be a -14 for x, and then a -12 for y. And now it does check out with the first equation. And it does check out with the second equation as well. So making sure you put the x and the y in the right spot are important. The key here again is to try to figure out what can you multiply to each equation. If you have to do more than one, that's okay, but what can you multiply to get the numbers to eliminate, or a variable to eliminate, when you add the two equations together. You guys have another one for elimination here, a third one for C. So let's go ahead and see if you can pause the video and see if you can use the elimination method to solve in C. Okay, so hopefully you had enough time to get an answer down there. First thing that we should do here is we should notice these are not written in the same format. So I want to make sure I rewrite them. So the 3x plus 4y equals 12. I'm going to rewrite the other one in the same manner. So 6x plus 8y, adding 8y to both sides, equals 24. Now what you may have noticed right here is that, okay, I can get, if I check the x's, let's go ahead and check the x's. I can get the x's to eliminate if I multiply by -2. So that gives me -6x minus 8y equals -24. And if you start noticing something right there, we can see that once we start to add these two equations together, what we get is actually 0 equals 0. And this is true, but it doesn't tell us anything about x or y. So what we know here is that both x and y are actually all real numbers. So this is going to have an infinite number of solutions. The solutions are going to be set by an equation. So if we rewrote one of these equations for y, and let's actually go ahead and do that. Let's do this graphically. Let's go ahead and rewrite these equations. So if I rewrite this first equation, it would be subtracting by 3x and divide by 4. So y equals -3/4 x plus 3. So type this in. Y equals -3/4 x plus 3. And then if I type in the same thing, so in this case I might subtract negative 24 and then divide by a negative 8. So this would be negative 6 divided by 8 x plus 3. If I take a look at the graph, here there's the first line graphing, and there's the second line graphing. We see no difference. The graphs are the same, and so the solutions are going to be created by this, the equation for this line. But any solution that's on part of this line is going to work. So what that takes us down to is what we call inconsistent and independent, or sorry, dependent, independent, inconsistent, and dependent systems. So most of the time, what we look at is like the first few examples, what we call independent systems. So independent systems are systems, basically, if we take a look at them graphically, they intersect in one location. So an independent system is going to have the slope from one line is going to be different from the slope from the other. So this is for any format of the equation y equals mx plus b. The slopes are going to be different. So if I were to sketch out a graph for these, and this is just going to be a rough sketch, but one of my lines could look like this, and one of my lines could look like that, and they intersect here, and there's one real solution. This is what we call an independent system. This is what we view most of the time. What we saw here, secondly, is what we call a dependent system. And so in this case, the slope is actually the same, and the y-intercept is the same. Both things are going to be equal. So if we were to graph this, and we did just graph that, but if we were to graph this, here could be the graph for one of my lines, and the other line would be directly on top of that. It would map in the identical pattern. So let's draw that one right in on top. And this one is going to have all real solutions. And then it would be determined by whatever that line was that we're viewing here if we simplified one of the equations. The final kind that we haven't looked at, this is what we would consider, or what we would call, inconsistent equations, or an inconsistent system. This is when the slope is equal, but the y-intercepts are not equal. So if I took a look at that graphically, if you remember back to Algebra 1 and geometry, if slopes are equal, but y-intercepts are not equal, these two lines are parallel. Okay, so that's not exactly perfectly drawn, but you get the idea. These two lines are parallel and they don't intersect, so there's no real solution. So, like we solved the last equation, problem number 3, we came up to a statement that was true. And so this would be a dependent solution. A dependent system. It has all real solutions. If we came up with a statement that was not true, maybe we came up with 2 equals 4. And we know that that's not correct. 2 does not equal 4. This would be representative of an inconsistent system here. So there would be no place where these two intersect. So we can have some cases where most cases systems have one answer that we're looking for, but some cases they do share all real answers, and then some cases there are no solutions for those. Okay, so these are the 3 methods that we look at for solving systems of equations: graphically, and then using substitution, and then using elimination. Now let's go ahead and take a look at what we're focusing on here, and this is systems and modeling. Again, this is not something that's relatively new to us, so it's more review, but we want to take a look at how some of these systems of equations work into word problems. So similar to like the first problem in the notes, there was a word problem, we set up 2 equations, and we would be able to now use those equations to solve. Let's take a look at problem number 5. 5 says, a jeweler is commissioned to create a piece of artwork that will weigh 14 ounces and consist of 75% gold. She has on hand 2 alloys that are 60 and 80% gold respectively. How much of each she use? So we will basically want to figure out the value for two different things. We want to know, let's say x equals the amount of the 60% alloy. And let's say y equals the amount of 80% alloy. So we can create a system of equations based on what we know here. We know that the piece of artwork will weigh 14 ounces. So this amount is going to be in ounces. So whatever the ounces is of x added to the ounces of y, the ounces of both alloys have to add together to give us 14 ounces. So that's our first equation. The other equation has to deal with the percentage of the gold. So remember that you take we can take percentage of gold by taking, or the amount of gold, sorry. We can take the amount of gold by taking the percentage times the weight to get the total gold amount. So let's say this is 60% gold and 20% silver or whatever else, but we want it to be 75% gold. So we know that the overall artwork is going to be 14 ounces times 0.75. 0.75 represents the percent for gold. So the weight of gold would be the 14 times 0.75. Well, how do we get the gold, or that weight of gold, from the 60% and 80% alloys? Well, 60% of a decimal is 0.6. So 0.6 of x and zero point 0.8 of y have to add together to give us this expression right here, 14 times 0.75. So now, here's our system. A couple different ways we can solve this. You could use the substitution. I'm going to go ahead and use elimination. I'm going to multiply this first equation here by 0.6, or negative 0.6. And I'm trying to use both of these two to solve the system because we know there's two variables. So this is the only way. If we have two variables, you have to have two equations. You have to create a system to solve. So if I multiply this first one by 0.6, or negative 0.6, this will give me negative 0.6x plus negative 0.6y. Sorry, let's make this a minus 0.6y. And then 14 times 0.6 equals negative 8.4. And then in the second equation, it's negative 0.6 still plus 0.8y, because I'm not really multiplying anything. I am going to simplify this 14 times 0.75. Give me 10.5, and now I can use the elimination method to solve here. So this would give me 0.2y. The 0.6's would cancel out. 0.2y, and then I'd have 10.5 minus 8.4 equals 2.1. So to get y by itself, divided by 0.2, so y equals 10.5. That is one of my solutions. So how do I find my other solution? Let's go back maybe to this first equation and substitute x plus 10.5 equals 14. I can subtract by 10.5, and so I would get 3.5. So we want to make sure that after we set up the system of equations, and in this case we're just going to use algebraic methods. Yes, we could graph these and find those intersections. We're just going to practice algebraic methods for right now for these problems. So once I go ahead and I set up my systems, I use my algebraic method to solve. I want to take these problems, or these values of the variables, back to the context. So we need 3.5% of, sorry, not 3.5%, sorry, this is talking about amount. So 3.5, our variable for amount is ounces. So 3.5 ounces of the 60% alloy. And we need 10.5 ounces of the 80% alloy. So if we do this, this will end up giving us a 14-ounce piece of artwork that is going to be 75% gold. Let's take a look at another example. Problem 6. Problem 6 is going to be a little bit different because we don't actually have two variables in problem 6, not two identical variables. It says Karen's at-home business makes large decorative candles for all occasions. Her costs include materials at $3.50 per candle and rent and utilities that average $900 per month. If her candles sell for $9.50, how many candles must be sold to break even? So here the only thing that we don't know in this problem is how many candles there are. So let x be the number of candles. And we're assuming that every candle that she makes is going to be equivalent to every candle that she sells. So to break even basically means that she's not making the profit, but she's not making any money. So what we want is we want her cost to equal her revenue. And so we can create an equation for this. What we can say here is that cost and revenue need to be equal, so we can make them the same variable. So if they're equal, we may not know what their value is, but it's got to be the same value to be equal. So let's just make cost and revenue equal y. Let's create an equation for cost. Well, her cost includes $3.50 for candle. So y equals 3.5 x. So 350 every candle, which is x. And we know that she's also going to have an additional $900 per month. So this is an equation to represent cost. An equation to represent revenue. Remember, revenue is the price times the number of sales. So the price here is $9.50 per candle, and the number of sales would be x. So y equals 9.5x. So we could solve this one by substitution or elimination. I'm going to go ahead and substitute since y is already by itself. So then I can take 9.5x and substitute it in for that value of y. So let's go ahead and do this algebraically. Again, we could do it graphically, but I'm just going to practice those algebraic solving methods right now. So 9.5x equals 3.5x plus 900. Should be fairly easy for us to solve this. Subtract 3.5x from both sides, so 6x equals 900. Divided by 6, x equals 150. So, excuse me, sorry. This question, sorry. This question only asked about the number of candles that are being sold. So all we had to figure out here in this case was x, how many candles are being sold. We don't need to figure out the cost or the revenue. It didn't ask us that, but we just know that 150 candles must be sold to break even. So here we use systems of equations because it gave us the variable that we were looking for, number of candles, and also knowing that cost and revenue was equivalent, so we could make them together the same variable for y. Now let's take a look at one more. This one's a little bit more complicated. Problem 7 says an airplane flying due south from St. Louis, Missouri to Baton Rouge, Louisiana. It's been a long day. An airplane flying due south from St. Louis, Missouri to Baton Rouge, Louisiana has a steady tailwind to help complete the trip in only 2.5 hours. On the return trip, the same wind slows the flight and it takes 3 hours to get back. If the flight distance between the cities is 912 kilometers, what is the cruising speed of the airplane, which would be the speed without wind, and how fast is the wind blowing? So, two things that we need to find here. Let's let A equal the rate of the airplane. This would be the cruising speed, how fast it's moving. Let's let W equal the rate of the wind. So these are the two things we don't know, the two things that we're trying to find. Now remember that distance is equal to rate times time. This is something that an equation you guys have used frequently in math and in science. So how are we going to create a system of equations from this? Well, there's two trips that they're taking. They're going from due south, from St. Louis to Baton Rouge, and they're coming back due north from Baton Rouge to St. Louis. So the trip there took 2.5 hours. So that's the time. But the rate is the little bit of a complicated part here. So we need distance. Actually, let's go back to distance. Distances are there for us for both. The distance is 912 for both of these, no matter which way it went. So let's say going from St. Louis to Baton Rouge, that's 912. The time is 2.5 hours, but what's the rate? Well, there's a tailwind that's helping complete the trip. So the speed of the airplane and the tailwind together are pushing in the same direction. So the rate is actually going to be the A plus W. They're adding together. And it's taking 2.5 hours. So if I simplify this equation, I'm going to write it over here for my system. If I simplify this equation, 912 equals 2.5A plus 2.5W. Now on the return trip, still 912, still 912 miles. But this time, the wind is blowing into the airplane. It's reducing the speed of the airplane. So it's not adding to it, it's taking away. So this would be A minus W times 3. If I simplify this equation, 912 equals 3A minus 3W, and there's my system. So to solve this system, a variety of different ways you could go about it. Let's go ahead and use the elimination method. What I'm going to do here is I'm going to notice that W in one is positive, negative in the other. So what I'm actually going to do is just multiply by the coefficients here to get rid of them. I'm going to multiply the first equation by 2.5. I'm going to multiply the first equation by 3, use their opposite coefficients, and the second equation by 2.5. So 912 times 3, this would be 2,736. 2.5 times 3 would be 7.5a. 2.5 times 3 again is 7.5w. 912 times 2.5 is 2,280. 7.5a minus 7.5w. So now I can add these two equations, and that's going to eliminate the w variables because they here have opposite coefficients. So if I add the 2,736 and 2,280 together, that gives me 5,016 equal to 15a, where I take 7.5a plus 7.5a. Now I can divide by 15 and figure out that a is 334.4 kilometers. And again, you could, or kilometers per hour. We'll come back to units a little bit. Again, you can type that into your calculator to get these computations. So I have done this already, but you can take 3 times 2.5, 3 times 912, 2.5 times 912, add these together, divide by 15. You can do all that in your calculator. Now let's go ahead and figure out how we're going to come up with W. Well, once I know one of the variables, I go ahead and substitute back in to find the another. So let's go ahead and just do 912 equal to 3 times A, which is now 334.4, minus 3W. So I would simplify this. 3 times 334.4. So 912 equals 1,003.2 minus 3W. So you can take 912 minus 1,003.2. So negative 91.2 equals negative 3W. Divide by negative 3. And W equals 30.4. So now I have the answer for both variables A and W, and I did need to solve for both of them. I want to put those back into the context. So the two things that I was trying to figure out was the cruising speed of the airplane. So airplane cruising speed was A, so that was 334.4, and this was in kilometers an hour, so kilometers per hour. Finally, the wind rate, or the rate at which the wind was blowing, was 30.4, and this was again in kilometers per hour. So there we have it. These are the ways in which we will use systems of equations, or how we can use and how we can solve systems of equations. We have the three methods. We have solving through graphing, we have solving through elimination, and we have solving through substitution. We want to be able to use all three methods. So you can see here in problem 7 I used elimination. In problem 6 I used substitution. You're not necessarily always going to be told which way you have to do it, but sometimes it saves you some work in some certain cases. Again, none of this should be brand new material. This should be a review, pretty heavy review from Algebra 1. So at this point, that is the entire content for SE1 notes, which is, again, solving linear systems in two variables. You guys will have a homework assignment posted to Google Classroom. So let me jump over here on Google Classroom. This is grayed out right now, but eventually it'll become live under SE1. You'll have the notes packet. You'll have this video. On SE2, you will have SE1 homework here. You'll have your homework assignment, and then you'll have your additional resources available to you. So after you've taken notes, you finish this video, you guys should work on your SE1 homework, and then we will get together again here soon for a Zoom session before taking an assessment over this content. If you do run into any questions that you want to ask before that we get on Zoom, shoot me an email. Thank you guys for tuning in, and have a good day.